Continuing with the grade 11 general practice questions for physics, and we are now looking at waves. Transverse wave is the perpendicular one. Transverse wave is basically a wave that goes like this, but it's actually moving along in a straight line. So it's going up and down. These particles are moving up and down, bobbing up and down. They actually don't move to the right, they just stay up and down. So this is the particles move perpendicular. This is perpendicular. 90 degrees is perpendicular. Perpendicular to motion. That's the idea here. And an example of that, well, we have water waves. Water waves. You have the Mexican wave. I'm not going to write that. You know the Mexican wave at the football stadiums when everybody raises their hands and stuff. You can say water. You can say light, radiation, things like this. And what else? Longitudinal wave. That is like sound, for example. This is when you have compressions, rarefactions. It gets rarer, and then it becomes to compressions again. So they're moving back and forward, back and forward. That's how the particles move, and the energy gets transferred to the right. I showed you this in the lab with the slinky. So it's basically like that. The particles move parallel, same direction, parallel to the motion or the wave. I should have wrote wave. It doesn't matter. Okay. Now that means an example. I've said it already. I've said an example: sound waves. Sound waves. You also have the earthquake waves. I think we call that P waves. P waves from the earthquakes. Compression, rarefaction, extending. This is going to be moving back and forward, back and forward. We call that a longitudinal wave. Very nice. What is the name of the area of low pressure in a longitudinal wave? Low pressure, that is when they are not close together, they're quite far away. That is this part here, that's low pressure, and we call that rarefaction. Compression is high pressure when they're really close together. Crest and trough, those two are for the other waves, the transverse. Alright, so now what we're doing is drawing random lines. Let's get rid of that. So we have a displacement versus distance and a displacement versus time graph, both of these. So we can learn different things from each one. From the left one, I can learn the wavelength. From the right one, I can get the period. If I know the period, I can find the frequency, by the way. I can even find the amplitude as well. So let's see, it depends what the question wants. What is a period? Okay, very nice. So period is the one related to time. So period is 1 over f. Period is 1 over f. So problem is, of course, well, we don't really know the f, right? We can find the f. Oh, well, we do know the period. Of course we know the period. We don't need to do 1 over f. Why would I need to do it? Because you can use the graph. What am I saying? This is the reason I mentioned this graph. The period is one complete wave. That finishes right here. The period, no need for the formula. If I asked for the frequency, I'd use the formula. So displacement, time here to here, that is one complete wave, and that's 0.3, 0.5, that must be 0.4. So the answer to that question must be 0.4 C. What is the wavelength of the wave? So I'm not going to use this one because that's time. This is the distance, this is wavelength, so I can go from the start to the top to the top. Top to the top, that is coming one complete wave, that is 0.6. So the wavelength, I will say, is D, 0.6. Very nice. And now I need to find the speed of the wave. The speed of the wave, that's fine. Speed of wave equals f lambda. Now I need to find the frequency. So let's go back up. I know this is my period. F equals 1 over t equals 1 over 0.4. Obviously 1 over 0.4 will tell you 1 over 0.4, that is simply going to be 2.5. 2.5. So now I'm going to write that into my formula. 2.5 multiplied by my wavelength, which I said was 0.6. As 2.5 times 0.6, I will get 1.5. So C is the answer, 1.5. So all that did was I found the frequency from the period by doing 1 over f equals 1 over t, and then after I did that I multiplied it by the wavelength. This is the wave equation, so I used that to get the final answer. Identify the quantities labeled. So A, this is going from here to here, that is a wavelength. B is what we call an amplitude. The height of the wave is the amplitude. So the wavelength and amplitude, the only option I can say would be D. And we're moving on to the next one. What is the amplitude of this wave? I'm guessing it's just, is there any numbers? Yeah, there are numbers. We have 0.4 here, so that is the top to the very bottom. I only need half of that. The amplitude would simply be 0.2. Why did I write 5? 0.2, because half of that. The wavelength of the wave, I need to know the full wave. So now what we have 1 1/4. So that's kind of sneaky, isn't it? So the full thing from 2.5 to here, that's not good. So we need to figure out what a full wave, which is only here for. So what I'm going to do is I'm going to take this wave 2.5 multiplied by, not multiplied by because I'm dividing it. I'm not trying to find the wavelength. So divided by 1.25. So 1 1/4 I can write 1/4, or if you know that means 1.25. 1/4 is a quarter, which is 1.25. I hope you get that. This is just a quarter of a wave. That's half a wave. That's a quarter, and the line stops right here. So I'm going to take my 2.5, I'm going to divide that by 1.25, and I will get simply 2. So the wavelength is 2 meters. And it kind of makes sense. If I break this up into quarters, each one into a quarters, you'll get 0.5, 1, 1.5, 2, 2.5. So that makes 2. Very good. You can divide into 5 parts. So many ways to get the answer, that's enough. Identify any 2 points on the wave that are in phase. So that basically means anything that is in the same position. Now let's get rid of all of that stuff again. And let's check. B and X, that's a good one. So that's fine. D and J. A, not D, because it has to come all the way back up. A and G is good. A and G is good. And then, is there anything else? There's probably more as well, to be honest, but I hope you get the idea. C coming down, and then I is also coming down. C and I. These are all at the same position on the wave, the same place. Okay, very nice. Let's move on. The diagram, I didn't write it in the box, but you get the idea. The diagram below shows 2 points, A and B, moving on a wave train. How many wavelengths separate A and B? Let's check. So this is 1 and only a half. 1 1/2. That's one full wave, and that's half a wave. So 1.5 is fine. Alright. Find the values of the quantities listed in the tables below for each. So let's find these values. And what are we looking for? Amplitude of wave 1, that's the height of wave 1. We know that is simply 10 centimeters. Wave 2, the height of wave, that's only this high. That's 5 centimeters. The period of wave 1, so this is a time graph, so that's fine. So one full wavelength, period for this one at 0.4. 0.4. The next one goes all the way and it ends here. Yes it does. That's 0.8, I will say. 0.8. Frequency, that's simply F equals 1 over 0.4. And I think I did that earlier, didn't I? 1 over 0.4, and that was 2.5. 2.5 hertz. And over here, I'm going to do 1 over 0.8, and that will simply be 1 over 0.8, 1.25 hertz. Period, we should write seconds, and amplitude, the centimeters. Don't forget your units, you will lose marks for units. I mark very harshly if somebody forgets units. One of my students knows what I'm talking about. Okay, so let's see what's next. What is the light? What is light? Light is simply a wave. It's not an electric wave. It's an electromagnetic wave. It has an electric field and a magnetic field perpendicular to each other in a big packet, and it moves. So electromagnetic radiation. Difference between opaque, translucent, and transparent. Okay, we're reaching the end, I think. Windows at home gives a clear view of outside, and what do we call that type of window? If you want to be able to see through the window, of course it's going to be transparent. If you want to see a little bit, like frosted glass or privacy windows, something that blocks some of the light, we can call that translucent. Opaque is when it's like a wall, a solid wall. You cannot see anything through it. That's opaque. Reflector is just something that shines light back at you. Okay, a little bit like opaque, because opaque kind of does that too, but reflector shines it more. Let's look at this next question over here. We have opaque material, so we can see for opaque, it absorbs some light, which means it reflects most of the light. Not some light, it will reflect most of the light. In fact, it should reflect all of the light. I don't even know why they're saying some light, because it blocks all of the light. Most light is what I should be saying for this one. Transmits, none. None. Because this said some, I wrote most. This should have said, yeah, well, I suppose it does absorb some energy. Oh, okay, I accept it. Translucent materials. Translucent materials, what does it do? So that is half and half. It absorbs some light, and then it will reflect some light as well. And it will also transmit. Some light will also go through. Some light. That's like a window that is not fully clear for you to go through, like a window blind or a curtain, and you can see through it. So it will scatter the light, and some light will be absorbed and some light will be reflected. So now I can see why it's saying absorb and reflect some and some. I see that now. Okay, transparent material. Transparent material, this is something that allows the light to go through. So maybe as the light goes through, it will block some of the light. Not block, but absorb some energy, just like we're doing over here. So clearly there is some light being absorbed, some light. And it's not supposed to reflect any light, but clearly sometimes if you change your angle, you can see a reflection. It does sometimes reflect a little. So I'll write some light for reflections, because you can see reflections through windows as well. Some light. So that's why that's an L. Some light. When light no longer travels in a straight line, so when does it? So that's when it goes through something on a straight line. Either it goes through some sort of translucent material, like it will scatter, or when it hits the boundary. So for example, if I have a translucent thing and it goes that way, it will scatter in different directions perhaps. So it will move in different directions. It begins to scatter in odd directions. And that happens when it reaches something. So from air into a glass, that's a boundary. So we call that a boundary. This is another word that we can use called refraction. You may have done refraction in previous years. So when it hits a boundary, this is refraction of light, or when it hits something translucent. Oh God, there's still 2 more questions. All right, let's do them. What's the correct formula for a point source illumination? Well, I guess there's not really much to say here, because it's kind of just right there, isn't it? P over 4 pi r squared. Nothing crazy there. I'm guessing in an exam it will just give you these options over here. So 4 pi r squared, well that's wrong. Well, it's going to be wrong because this is the relationship. What can I say? Not much else to say. What best describes the relationship between distance and illuminance? The illuminance, well, as you can see, E equals P over 4 pi r squared. It's asking for distance. Distance is r. It's dividing by r, like I mentioned earlier. Dividing means inversely proportional. Inversely means 1 over r. There's an imaginary 1 above it. 1 over r squared. 1 over r squared must be d in this case. That is the correct answer. It's inversely proportional to 1 over r squared. And that's the end of the lesson. Thank you.